What if I told you a black hole, defined as a region of space having a gravitational field so intense that no matter or radiation can escape, actually radiates energy and becomes smaller because of it? But before that, let's talk about the Large Hadron Collider. In 2008, scientists built a machine that would collide beams of high-energy protons or ions to mimic the conditions that existed moments after the Big Bang. These particles would circle a 27-kilometer long ring that would accelerate them to more than 99.9999% the speed of light, and will crash into other particles, creating many particle building blocks that scientific instruments can detect. However, some people were concerned that the collision of the particles at that high of a speed would create a miniature black hole at the center, and with the destructive nature of black holes, it would grow bigger and devour the Earth, spelling doom for humanity. Now, of course, this did not happen, but to understand why, we need to get smaller. Smaller than an atom, smaller than an electron, until we get to the quantum level, where we could observe the quantum foam. In 1955, John Wheeler coined the term quantum foam to describe the constant chaos and activity in apparently empty space. Essentially, at this level, particles and their antimatter counterparts can spontaneously appear and instantaneously annihilate each other, but still be able to interact with the universe during their lifetime. The famous quote from Albert Einstein, "Energy cannot be created nor destroyed," is quite conceptual in the scale we live in. However, as we get smaller and reach the limits of observability, the fundamental law of energy becomes quite fuzzy. When the particle and its antimatter counterpart appears, it owes energy to the vacuum it appeared in, and must return that energy before the Planck second. The amount of Planck seconds in a second is more than 5, followed by 44 zeros. However, in 1974, Stephen Hawking theorized and coined the term Hawking radiation, where black holes would radiate energy. The argument theorized that when a particle and its antimatter counterpart appears too close to the event horizon of a black hole, one particle can be dragged in or fall into the black hole, leaving just one particle that cannot annihilate with its antimatter counterpart anymore. This violates the fundamental law of energy, so quite literally, our black hole is in debt, energy debt, and the only way to relieve this debt is to release the energy as radiation. This is why even if a miniature black hole were to form in the Large Hadron Collider, it would disappear within moments of being created. So to this day, black holes have not broken the laws of physics as we know it, at least not yet.